Hello everybody and welcome. In this video solution, we are going to talk about the problem reachable nodes in subdivided graph. It's a hard labeled problem and as we'll soon see, it deserves to be called so. I'm going to break this problem down to 3 components and each of them is going to flow into the other, so everything will make sense at the very end. Okay, to be on the same page, let's talk about the input-output and then we'll get started with the components of this problem. The first thing we want to note is the edges. So the edges are given as x, y, c format and a list of all of these tuples. So x, y, c basically says that between a node x and a y, there exists an edge. Okay, it's an undirected graph, so there is no direction to this edge. So between x and y, there lies an edge. And in this edge, we are going to now insert c nodes. So for the purposes of this solution, I'm going to call x and y as big nodes, the original OG nodes, and we'll have c as small little nodes present inside of this edge. Okay, I'll explain more in a bit. Then we have the max moves, which specifies sort of how much you can explore the graph. What is the number of steps you can take? And if you have exhausted all of your steps, you can't go any further and you can't explore any further. So maximum move sort of restricts you to a sort of a radius in which you can explore the graph. And you are also given n, which is the number of nodes. The goal is to return this integer, which is the number of reachable nodes in the subdivided graph. Okay, so the first thing I want to talk about is count as cost. Okay, let me explain. See, max move specifies how much you can explore in the graph. Let us call that as a budget. We have the budget available to us and we can spend that budget anywhere we want. How do we spend that budget? Well, let's look at a case of x, y in the original graph where we haven't inserted those c nodes yet. We just have x, y and an edge between them. What is the cost of going from the node x to the node y or vice versa? The cost is just going to be equal to 1. Right, because you take an edge, you travel that edge, so some of your budget has to be spent here. So the cost is 1. For each and every single edge, the cost is going to be 1. And this fact becomes important very soon, because as soon as we add those c new nodes, inside of between the edge between the x and y, what is the cost of the same edge from going x to y? Right, I want to know how much it takes for you to go from x to y. So what is the total cost? One edge gave us a cost of 1. When there are c nodes inserted, we'll have a total of c plus 1 edges, which means that the cost is going to be c plus 1. What I've basically done is I have sort of forgotten about what the small nodes are and I'm only looking at what is the number of edges they broke it down into. Alternatively, I can say that this cost specified how much this weight cost, how much this edge cost. In other words, I'm looking at it as a weighted edge now. The original question was not a weighted edge, by the way. All of them had the cost of 1, it is not weighted. But for the purposes of our implementation, we're going to look at them as weighted edges. Again, at this point, I am not focusing on the small nodes, just the giant nodes x and y. And so naturally the question comes, see, we have small nodes, large nodes. How do we count? Like, our goal is to return what? The number of reachable nodes. And what is the number of reachable nodes? Well, it's the number of big nodes you can reach and the number of small nodes you can reach. Pretty simple. And so we'll now talk about them individually. Okay, how about we talk about big nodes first? So the count of the number of big nodes we can reach is, how do we find that out? Let's take a very small case. Let's say that we have this node 0, 1 and 2 here. There are a bunch of nodes inside of here. We don't care about them. Let's say that from the node 0 to going to the node 1, let's say we encounter some cost. You know, there's a long path and you finally reach from like long journey to 1. And that takes the cost of 11. Fine. What if you find another path from 0 to 2 to 1? You find a new path which is apparently taking the cost of 3 plus 4. Now the original cost you had was 11 and now there is a new path coming up with the cost of 7. Which one do we pick? Like, we have to reach the nodes, we have to make a decision of which path to take, right? And here we'll pick the cheapest path. And the intuition behind cheapest path is that, look, we are starting with a fixed budget, right? We can't increase that budget. So if you spend cost 11 in reaching to the node 1 when you could have spent 7 to reach to the exact same node, why would you take the cost 11 one? You just take the cheaper route, get to the same place. And then, since you have more budget left in the second case, in the case of 7, you can maybe explore more nodes. So logically speaking, the cost 7 is a better alternative than cost 11. So there are two things that are happening. First is that we're starting from 0 always, as the question specifies. Let me just point it out to you here. You want to know how many nodes are reachable from the node 0. And so we're starting off from 0. That's the first point. And the second point is we want to pick the cheapest path. Alternatively, we want to pick the shortest path to any particular point. And this leads me to this idea. Is the single source shortest path algorithm, also Dijkstra's algorithm. And this is one key observation of this problem. Look, we want to reach to all of the nodes, right? We want to look at how far away these nodes are so I can decide whether I have enough budget to go to them or not. Now the way I define and find out the distance from me, the 0 node, to all of the other nodes in the graph is how do I find out the distance between me and all the other nodes? It's by using Dijkstra's algorithm, which will get me the shortest path to any particular node. I'm not going to go into any more details about this algorithm. I'll just link to a couple of links below. And yeah, so at the end, what we'll do is we'll start off the answer, which is counting the big nodes, which is the part 1 of it, as the sum of all of the nodes I, which have the distance less than equals to maximum moves. Basically, all of their distances are in our budget. So we have split out these nodes into big and small. And so we'll find the answer to the big nodes first, and we're able to find this answer. But this is only one half of the story. What about small nodes? This can get a bit more complicated since it's most mathematical part of this problem, and yeah, it's just basic max, min and stuff like that. Okay, let me explain. Let's say that, again, we're looking at this abstractly. Let's say that we have two nodes x and y over here. Fine. And there's an edge between them at the cost of w. That's also fine. Let's say that from the node 0, I'm starting over here, and let's say I'm starting from the node 0 above, and I reach to somehow x here and y here. I'll take two different paths to come to x and y, and each of them will cost me certain amount. Let me just say that wx is my remaining budget, and wy here is my remaining budget for the y point. So in this particular edge between x and y and these w nodes in the middle, I want to find out how many small nodes can I access. That is saying that starting from wx over here, how many small nodes can I access? Has wx enough budget to cover the entire w, or does it not have enough, so it will only cover subset? Or maybe y has enough budget to cover the entire thing, or maybe y doesn't have. Let's enumerate the cases first. So two very basic cases come out first. Look, if either of them have greater than w cases, if either of them have greater than w budget, then we can use either of them to cover the entire range, right? You have wy budget over here, and let's say that wy is greater than w. So what you'll do is you'll spend all of your budget and you can reach the point x over here. That's our goal. So we can cover all of these nodes here, and we can spend all of our budget on these guys. So in either case, if wx is greater than w or wy is greater than w, answer gets increased by w. Okay, this is one case. What if both of them are lesser than w? Let's actually enumerate this case further and we'll see two more cases pop up. First is the case where Wx is like somewhere over here and Wy is somewhere over here. Both are disjoint sets. So what is the total coverage of these guys? Is just Wx plus Wy. Okay, that's fine. It's still not equals to W, but sure, we are sort of getting there from the right and left sides. What if Wx is less than W and Wy is less than W, but both of them combined together go over the range? So in this case, what's happening is Wx is certain thing over here and Wy is certain thing over here. Both of them have this overlapping section, which means that if you look at the total, you are sort of overflowing the range of W. So we'll just add W because there are no more nodes than W in this range to explore. So we'll just put W as the answer. So we have found three things. You do either answer plus equals to W when this case happens, or you do answer plus equals to Wx plus Wy, or you do answer plus equals to W again. This is a bit complicated and I'm not sure how we could implement this, but let's actually take a look at a more mathematically dense format, which is going to make our life a lot easier. Okay, this is very sneaky but smart as well. What I'm trying to do here is, let's say that I write the worst possible case where we are not able to cover the entire range. So we have Wx plus Wy and we'll store that in the answer over here. What I'm trying to do here is I'm trying to find out the range which overflowed. In this case, there is no overflow, so this will simply return 0. Right, what's happening here is I'm calculating Wx plus Wy minus W. I'm saying that, you know what, give me Wx, give me Wy, and I'll reduce W from it, which will get me the range that overflowed, which will give me the portion that sort of water that spilled out of the glass while I was filling the glass with the jug, basically. Okay, at this point, this makes sense. Okay, you can do Wx plus Wy minus W, comma 0. So it will always basically be 0 for this particular case. But for cases like these, and for the cases we saw above, where both of them or either of them are greater than W, this case is also able to handle for that. Feel free to pause and write down stress test this guy, and with this we can wrap our solution up. This is exactly it. So what we're doing is two things. First, we are going to implement this Dijkstra's algorithm. This is the first thing, and the second thing is we're going to just iterate over all of the edges, and we're going to find the number of nodes which we can access inside of a particular edge. So two-part solution and we'll be done. Well, actually it's not two parts, it's three parts, because the first part is actually creating something we can use. Dijkstra's algorithm uses an adjacency list, so we'll actually have to go get started with that. I'm going to create as a default dict of I want adjacency list is of the format element here, and then we'll have a list of element here and the weight here. This is the format we want to follow. So it's going to be a default dict of list. Cool. Now I want to iterate over all the edges. So we'll have X, Y, and C as the count in edges. Adjacency list of X is going to be appended with Y comma C. By the way, is Y comma C correct? Let's do a quick check over here. What is the cost? What is the weight of this edge? Is it C or is it C plus 1? It's C plus 1. So we'll actually do that correction over here, and then we'll do the copy pasting thing because this is an undirected graph. Yay, copy paste. Okay, cool. We're done with creating the adjacency list. So the second thing we want to do is implement the Dijkstra's algorithm. So let's have a heap here, which is going to be a tuple of distance and the node. So this is in the format of distance node. Cool. We'll do while heap exists. while there are elements in the heap, while there are nodes left to be explored, we'll go ahead and explore the nodes. So heap pop from the heap and get me the elements, which is going to be distance and the node. And this is where adjacency list comes into play. As we saved it earlier, we wanted to know for any given node what are the neighbors of it. So we'll do for this is going to be what we stored in the format of x comma w. So we'll have neighbor and weight in adjacency list of node. For each of these, what do we want to do? I want to say that, you know what, let's just try getting to the node neighbor. For getting to the node neighbor, what do we have the total cost as? The previous node gave us a cost of distance d, and the current one is trying to give us a cost of w, right? The previous guy gave us a distance of d up till now, and we want to add w to it to get to this neighboring node from this particular node. So this is the temp distance. And we'll ask, hey, if the distance for the node neighbor is actually greater than the temp one, if you can find a lesser value for this distance, then go ahead and please save this, because this is a good distance. This is the cheaper one. So we'll go ahead and save that. At the same time, if you have found a cheaper route to a particular node, that means that you have more budget in hand. And so if you have more budget in hand, you can explore more nodes in the further, right? So we'll actually go ahead and do heap push this particular nay, and what else do we want to push? It's in the format of dist comma node. Okay, let's correct that then. It's temp comma nay or dist of nay comma nay. Okay, we'll also quickly create the dist here, which is going to be, well, it's a list of infinities. We'll initialize with that, but also we want to send the dist of 0 to be 0. Think about it. Why? If you've thought about it, look back to this point. We are starting from the node 0, so we have to set the distance from the node 0 to be 0, like trivial base case. Cool. At this point, we are done with the Dijkstra's algorithm part, and we want to find out how many big nodes can we reach. What is the equation that we used? Let's just do a copy paste. Answer equals to sum of distance of I less than equals to maximum. Okay, we'll do answer equals to sum of all of the places where the distance of the ith node was lesser than equals to max moves. And we'll do this for I in range of n. We'll do this for all of the possible nodes. Okay. Finally coming to the small nodes part. I know this will take a bit of time. Just bear with me. Okay. We'll iterate over all the edges again for x, y, and w in edges. This time, by the way, I'm not calling it count. I'm just calling it weighted edge, because that is what it is. And that is what we have used in the calculations over here. So let me just copy paste this equation again. We'll do answer plus equals to wx plus wy minus the maximum of the value that overflowed, which is wx plus wy minus w and 0. I think it looks correct. Cool, looks correct. So we first need to find the wx and wy themselves. How can we find that out? This is the budget remaining at the point x and y. So the budget remaining is basically max moves minus the distance of the current guy. Basically, out of max moves, you already expended the distance of x amount of budget to get to the point x, right? The distance, the point x was some distance away from 0, so you expended all of that to get to the point x. Similarly for max moves of minus distance of y. There's a small issue hidden here. We're not yet done. There's a small issue here. And the small issue is, this works only when wx and wy are both positive. what I'm trying to say is we have certain amount of budget in wx and wy to begin with. Both of them are greater than 0. If wx is greater than 0 and wy is greater than 0, then we are trying to do this. What this case will not work in is the case where one of the values is negative. Now think about what could be the case where the value is negative. If you think about the very original thing that I mentioned, when we are doing this max moves things, when we are doing this budgeting thing, we can only explore sort of a radius or a portion of the entire graph. There are still some nodes which may be lying outside of our reach, which are too far away for this budget to cover, even when we are considering the smallest distances thing. They're simply just too far away. In that case, to reach to that point will get us budgets negative. If you look at it, we've already expended, we have max moves budget, and to get to the farther away point, this entire thing would go into negative. So we somehow need to deal for that as well. And what we can do is we can do answer plus equals to, let's just say maximum of wx comma 0 plus wy comma 0, or maximum of wy comma 0. Okay, so what I've done here is I'm trying to say that, you know what, if both of them are negative, just screw them, I don't care about them, right? You can't reach either node, so it's no use for us. But if you could reach one node and not the other, if you could reach the x node but not the y node, then you still have some place to explore, right? So in that case, you would actually want to store the wx or wy. But at the same time, that wx or wy may be out of range. Like wx may have too much budget, so it will sort of cross over the entire range and then overflow. Think about why that case will never happen, why the overflow case will never happen. Because at this point, we are done with this problem. I'll go ahead and run this. This is actually a very interesting problem. So, okay, wait, let's just fix this. Heap push expected 2 arguments, got 1. Okay. All right. So you actually want to specify the heap as well. Cool. 23, cool. Let's just submit this. No, wrong answer. Okay, cool. So I'll take a quick break, debug this thing, and we'll get back. Okay, cool. So I figured out the issue that was there. The only case where we want to look at this particular case and where this will not work is when these budgets are negative. So we'll actually have to include the equals to 0 case as well. And so doing just that, I'm just going to show it again, is getting us accepted. Okay, cool. So this is it for the solution to the problem, reachable nodes in subdivided graph. And as always, thanks for watching.